Let's jump right into the fascinating world of metallurgy. We're going to look at exactly how we stop massive engineering structures from facing total, catastrophic failure. Whether you're studying to build the next generation of skyscrapers, designing aerospace components, or just kind of curious why the machines around us don't spontaneously fall apart, you are definitely in the right place. In today's explainer, we're breaking down material testing. We'll look at how engineers establish the absolute limits of materials and how they inspect finished parts without destroying them in the process.
Now, how do you know a bridge won't collapse before we even build it? This is basically the ultimate engineering problem, right? Because while metals are uniquely plastic, meaning they can bend, under the wrong kind of stress, they totally break. As structural materials, metals are incredible because they can be deformed. Think about a paperclip. You can bend it back and forth a bunch of times before it snaps. That is plasticity in action. But if we push a material way past its elastic limit, it just keeps deforming until it eventually fails. So the big question is, how do we predict that exact moment of failure before thousands of cars drive over our newly designed bridge? Well, when structural materials lose their ability to deform, we get what's known as brittle fracture. And our job as engineers and analysts is to test for these exact breaking points. Most nonmetals, and occasionally some metals under special circumstances, totally lack plasticity. They don't bend, they don't warn you, they just snap. Think of dropping a glass on the floor. It doesn't stretch, right? It shatters. Understanding exactly when and why a material will experience a brittle fracture rather than a safe, predictable deformation, that's literally the entire foundation of mechanical testing. So here's our roadmap for today. 1. Preventing catastrophic material failure. 2. Destructive testing, pushing those limits. 3. The danger of metal fatigue. 4. Non-destructive testing, which is basically our X-ray vision. And 5. Choosing the right test. All right, jumping into section 1, preventing catastrophic material failure and the search for uniformity. The primary goal of testing isn't just about safety. It's also about maintaining the exact uniformity of a material once we've nailed down a solid design. We really need to know that batch A of our steel behaves exactly the same as batch B. Now, the quote here hits the nail on the head. While real-world testing is perfect, time and cost limits mean we have to simulate these conditions in the lab. We can't realistically build a full-scale suspension bridge, drive a massive fleet of fully loaded semi-trucks over it until it collapses, and then be like, all right, cool, let's build the real one 10% stronger. It's just not economically feasible, so we have to rely on data from small test specimens. But as any good engineer knows, you got to accept that data with caution unless you are absolutely certain the test simulates actual service conditions. Moving into section 2. Destructive testing, pushing limits, and breaking things on purpose. This brings us to the crash test dummy phase of engineering, where we literally sacrifice a prototype to establish our baseline limits. In this phase, we take a sample piece of metal and completely tear it apart, crush it, or twist it until it fails, just to find its static mechanical properties. There are 2 main ways we break things out in the field, with a steady, static pull, or a sudden, dynamic smash. A static load is kind of like slowly standing on a diving board. The stress is applied steadily. A dynamic load, on the other hand, is like jumping up and down on that same diving board. It's suddenly applied or pulsating. Materials react very differently to these 2 types of stress, so we really have to test for both. By using common static tests, we determine the raw physical properties and the resistance of a material to a steadily applied load. This allows engineers to design safe bridges all over the world. For example, tensile strength tests pull a material apart to see exactly how much force it can take before snapping. Hardness tests measure resistance to indentation, and they're extremely popular because they are cheap and fast. And because these tests are relatively standardized, steel of a satisfactory quality tested and manufactured in France can be safely used by an engineer designing a bridge in Japan. The math translates perfectly because the static test data is basically universal. All right, section 3, the danger of metal fatigue and the threat of repeated stress. So what happens when the load isn't steady and instead pulses over and over again? This is where we enter the really treacherous territory of dynamic properties. It's been estimated that a staggering 95% of all metal failures are actually caused by dynamic loads, which makes endurance strength absolutely critical. Let that number sink in for a second. 95%. It is incredibly rare for a machine part to fail just because a steady, static load was too heavy. Instead, parts fail because they're repeatedly pushed and pulled, vibrated, and subjected to fluctuating stresses over a long period of time. This repeated loading causes a phenomenon we call metal fatigue. To test for this, metallurgists use tools like the Moore high-speed machine, which brutally applies repeated dynamic stress to a specimen. This machine spins a metal beam at super high speeds while applying a bending weight to it. So every single time the piece rotates, the top is stretched in tension and the bottom is squished in compression, and then they swap. It subjects the metal to literally millions of cycles of reversed stress to see exactly how long it can survive before just tearing itself apart. The result of that repeated stress is complete structural failure. Submicroscopic cracks form, they spread, and ultimately cause a catastrophic break. It usually starts at a minor defect, maybe a tiny scratch or a sharp corner where stress concentrates. Eventually, the microscopic atomic bonds break. As the machine keeps running, that tiny crack spreads inward. It's honestly like a disease. Finally, there's so little sound metal left that the remaining material simply can't handle the normal operating stress, and the whole piece fractures violently. Moving on to Section 4, non-destructive testing, our X-ray vision, inspecting without destroying. Imagine you've just finished machining this massive, multi-million-dollar turbine shaft for a power plant. You can't exactly put it in a tensile machine and snap it in half to check if the inside is solid, right? You need a way to look inside the metal without altering its physical properties. Non-destructive testing, or NDT methods like radiography and magnetic particle detection, basically act as our X-ray vision. They find malformed grain structures hidden deep inside expensive machine elements. These hidden flaws act as stress razors, those exact spots we just talked about where fatigue cracks love to start. By using X-ray radiography on large forgings and castings, or employing magnetic particles, we can spot internal voids, blowholes, or bits of trapped slag long before the part is ever installed in a working machine. To visualize the invisible, a sonic tester works in 4 pretty elegant steps, using compression waves to map out the exact depth and location of a hidden defect. You place a quartz crystal on the metal, often on top of an oil film. It sends high-frequency vibrations right through the part. When those sound waves hit the bottom of the part, they bounce back and show up on a screen called an oscilloscope. But if there is a hidden internal crack halfway down, the wave bounces off that crack early. This creates a sudden spike, or a pip, on the screen. By simply measuring the distance between the top surface reflection and that pip, you know exactly how deep the flaw is. It's brilliant. We can even use surface waves on curved geometries, like checking the fillet areas of a completely assembled machine shaft for hidden fatigue cracks. This is a real game changer. Using specialized crystals or plastic wedges, we can actually send ultrasonic waves to follow the curved surface of a part to reach spots we literally cannot see. And the best part? The machine can be completely assembled. You don't have to tear down a massive engine just to check if a highly stressed fillet has started developing a fatigue crack. You can test the whole shebang right there in the field. And finally, Section 5, choosing the right test, synthesis and application. Okay, let's bring it all together. Sound engineering judgment requires knowing exactly when to use a crash test and when to use an MRI. As diploma students and future engineers, your job won't just be running these tests. It'll be selecting the most efficient, cost-effective, and safe testing method for a specific scenario. Our core takeaway here is this: use destructive testing to establish baseline design and safety parameters, and deploy non-destructive testing for quality control and field maintenance on assembled, working systems. If you're designing a brand new bridge, you use tensile and notched bar impact tests in the lab to prove your steel is strong enough and won't fail via brittle fracture. But once that bridge is built, or once a pressure vessel is full of fluid and actually operating, you switch to non-destructive methods like sonic testing to constantly monitor for internal cracks or gauge the progress of corrosion over time. As automated technologies and artificial intelligence advance, how will the next generation of non-destructive tools further revolutionize the safety and lifespan of our structural world? I'll leave you with that provocative thought to consider next time you drive over a bridge or fly in a plane. We've gone from simply breaking metals in half to using ultrasonic sound waves to map their internal atomic structures. Imagine what happens when AI starts interpreting those oscilloscope pips in real time on our infrastructure. It's a wildly exciting time to be entering the field of materials engineering. Stay curious and keep exploring.